Think of a thermistor, a portmanteau of thermal and resistor, as a thermometer that speaks the language of electricity. While a standard resistor tries to keep its value steady, a thermistor is purposefully dramatic. Its resistance changes significantly and predictably whenever the temperature shifts. How it's made. Thermistors aren't made of coils of wire like some resistors. Instead, they are made from semiconducting materials, usually metal oxides. The recipe. Manufacturers mix powders of metal oxides like manganese, nickel, cobalt, copper, or iron. Sintering. This powder is compressed into a shape, a tiny bead, a disc, or a washer, and baked at very high temperatures in a process called sintering. Coating. Once the ceramic-like material is formed, it's attached to lead wires and coated in epoxy or glass to protect it from moisture and corrosion. Internal working. The science. Unlike metals, where heat makes atoms vibrate and block electron flow, thermistors are semiconductors. In an NTC thermistor, the electrons are normally stuck to their atoms. When heat is applied, it provides the thermal energy needed to shake those electrons loose. These newly freed electrons become charge carriers, allowing electricity to flow more easily. To calculate the exact resistance at a specific temperature, engineers use the Steinhardt-Hart equation. To understand how a thermistor works internally in more detail, we have to look at the world of quantum mechanics and solid-state physics, specifically how electrons behave in semiconductors. The internal physics, the band gap secret. Most thermistors, specifically NTC types, are made from ceramic semiconductors. Unlike a copper wire, a conductor, where electrons flow freely like water in an open pipe, a semiconductor acts more like a bridge with a gate. The energy bands. In these materials, electrons exist in two main states. The valence band, where electrons are stuck to their atoms. They can't move to create electricity here. The conduction band, the highway where electrons move freely. Between these two is a band gap, a forbidden zone where electrons aren't allowed to stay. How heat changes everything. NTC. When a thermistor is cold, almost all the electrons are trapped in the valence band. Because no electrons are on the highway, conduction band, the resistance is very high. When you add heat, you are actually injecting thermal energy into the material. This energy kicks the electrons across the band gap and into the conductor.